Yes, so my name is Matt and I'm at the University of Queensland working with Tim and Netta, and also Josh, another PhD student on this project, what I'm going to talk about today. So the title of the talk is Overcoming the Repeaterless Bound in Continuous Variable Quantum Communication without Quantum Memories. Yeah, so I'm going to be talking about quantum communication. So quantum communication is the art of transferring quantum states from one place to another. So this is obviously going to be important if you want quantum computers to talk to each other. And also you can do things like quantum key distribution. So two trusted parties can set up a secret key using quantum physics. So unfortunately, for any communication protocol, there's going to be a limit to the rate as a function of distance. And this comes about due to the no cloning theorem, because it's impossible to copy quantum states. And so if you send a state between two places, then the loss in the channel, the no cloning theorem, or the fact that you can't amplify the state without adding noise, this means that there's a limit to the rate that you can do quantum communication. So the main errors in the channel is, of course, pure loss in quantum optics, and also other channel imperfections. So can we overcome these fundamental limits? Well, we can if we use quantum repeaters. So that's what I'm going to be talking about in this talk. So the idea for quantum repeaters is that you divide the entire distance into smaller segments. And then because now there's less loss in those segments, you can overcome the noise using either quantum error correction or purification techniques. So I've just got a little picture on the right here, of our planet with, you can imagine the internet that we have at the moment, and then also quantum links, which keep the internet that we already have secure. And when we add quantum computers into the network, then those quantum computers can talk to each other as well. So this is kind of the future that we're aiming towards. And then you've got satellites that orbit the Earth that can increase the transmission distance as well. So I just want to talk about discrete variable versus continuous variable. So discrete variable systems are like two-level systems usually. For example, an arbitrary state might be a superposition of 0 and 1. And an entangled state would take this form where you have 0, 0 plus 1, 1. Continuous variable, on the other hand, is the system is infinite dimensional. So you can write it in a discrete basis in terms of all, in quantum optics, photon number states. And the usual entangled state that we talk about is the two-mode squeeze state. So we write chi, which is a superposition of all photon numbers. So it's important to realize that dV is contained within CV. Although if we're doing an experiment, usually dV might be, at least in quantum optics, it might be the polarization of the photon. So if you're doing quantum key distribution, Alice might be sending Bob, but encoding the quantum information in the polarization degree of freedom in the photon. Whereas in CV, we're usually sending things like coherent states, or if you're trying to do error correction, then you might be sending superposition states. And you encode the quantum information in the quadratures of the light. So there are three so-called generations of quantum repeaters. So the first and second generations use probabilistic techniques to increase the entanglement. It works by Alice and Bob start with some entanglement, and they send one mode each towards the repeater node, which performs a Bell measurement. And this does entanglement swapping. So the Alice and Bob end up entangled, and it's probabilistic. So that way we can get around the no cloning theorem and we can increase the entanglement. So this is obviously impossible deterministically. So that's how the first and second generation repeaters work. The third generation uses quantum error correction. So you take your quantum information and you put it straight into a quantum error correcting code, and you send the entire code, and then you recover from errors at repeater stations along the way. So the third generation is nice because it promises very high rates, but of course it's extremely difficult to implement in practice. The best experiments that we have today for quantum error correction are only just starting to break even. Whereas the first generation of quantum repeaters are going to be the most easiest to implement in the near term. So I'll be talking about the first generation of quantum repeaters today. So if you're interested in seeing quantum key distribution working, this is a nice simulation of the BB84 protocol. So you can go to this link in your own time if you like. So the way it works basically is that Alice is sending qubits to Bob. So she encodes classical values 0 and 1 into a random quantum state chosen from the horizontal or vertical or the plus and minus basis. And Bob chooses a random basis, so either the horizontal, vertical, or the plus and minus basis to measure that photon. And the point is that Eve doesn't know which basis to choose. So if she tries to intercept and measure the photon, then she messes up the quantum state. Because Alice and Bob are going to call each other on the classical telephone at the end of the protocol to sort out which basis they actually chose. But then it's too late for Eve. So this is how quantum key distribution works. And in continuous variables, it's very similar. So Alice now, instead of sending single photons, she sends coherent states modulated in the X or the P direction. So this is analogous to position and momentum for a particle. So X is just the real part of the complex amplitude of the coherent state, and P is proportional to the complex part. So Alice chooses this random coherent state and sends it to Bob through the quantum channel, which we give to the eavesdropper, Eve. And if Alice and Bob end up with more information than Eve does, then they can distill a secret random key. So this is actually equivalent to an entanglement-based version. So if Alice prepares a CV entangled state, the two-mode squeeze state, chi, and then performs some measurement, then it's equivalent. So in this case, she would perform a heterodyne measurement. So in this setup, we use to prove the security of the protocol, or you can use this setup, for other things, for quantum teleportation. So this is the rate distance trade-off that I was talking about with quantum communication. So the ultimate bounds are shown in red. So the plot bound is the repeaterless. So this is the point-to-point bound. So if you have no repeater, this is the ultimate secret key rate as a function of distance allowed by quantum physics. So it's proportional to the transmissivity of the channel, eta. And if you have one repeater, then the ultimate bound is the upper red line. So that's the best secret key rate you can get if you have a single repeater, which is untrusted. So we assume that Eve has control of the repeater station. So all these other lines are some of the well-known protocols. So if we look underneath the repeaterless bound, the plot bound, we have the BB84 protocols shown in gray. And just above that, we have CV. So the point of this plot is to show that CV actually performs better, at least ideally, in the ultimate performance than any DV protocol. So that's another reason why I'm interested in CV. So if we look at the repeater protocols, the dashed line shown in green is the so-called twin field protocol. And it's a very nice protocol because you don't need quantum memories to scale like the single repeater bound. And the other lines that go with it are variations on the twin field protocol. So the question I'm trying to answer in this talk is there a protocol in CV that follows the green line? Because you would guess that the CV protocol that scales like the single repeater bound would be better than the green line, because that's what we see for the direct transmission case, where CV is better than all of the DV protocols. So yeah, just in summary of this slide, the PLOB bound is the best you can do without a repeater, and it's proportional to the transmissivity of the channel. And if you have a single repeater, then the secret key rate scales like the square root of the transmissivity of the channel. So I just want to talk about how noise acts on continuous variable states. So if you have a coherent state, pure loss simply pulls the coherent state towards the vacuum state without increasing the noise. If you also have excess noise or thermal noise on top of the pure loss, then you go towards the vacuum because of the loss, but you also increase the size of the noise. So you end up with a thermal state. So because of the no cloning theorem, it's impossible to noiselessly amplify the state. However, you can do it probabilistically if you have some energy cutoff. So for example, if I'm only allowed the amplification to work in some, small region of the phase plane, then it can work. And so on a coherent state, you noiselessly amplify the state. But if you've had excess noise, then the circle gets bigger. So this is actually really a real issue if you're going to use noiseless linear amplifiers in continuous variable protocols, because the thermal noise is amplified as well. So here are the three ingredients of a continuous variable repeater. So there are a few different versions of continuous variable repeaters in the literature, and they basically all have these three components. So the first step is to distribute entanglement between all of the nodes. So you take your CV state and you send one mode. So you keep one mode of the CV state in the node, and then you send the other one down the channel. And you do this between all of your repeaters and Alice and Bob. So the second step is to distill the entanglement probabilistically. And for that, you might use a quantum scissor, which is a good realistic way of doing noiseless linear amplification. But there are other ways to do entanglement distillation. You can do, photon subtraction, or So, and then the third step is entanglement swapping. So after you've increased the entanglement of all the links, then you do some Bell state measurement to swap the entanglement. So eventually the end nodes, Alice and Bob, are entangled. So the key point here is that the entanglement distillation step, they all have to operate independently in terms of the success probability. So we need quantum memories to hold on to the quantum states. And then once all of the entanglement distillation steps have succeeded, then we do the entanglement swapping. So putting all this together, this is our continuous variable repeater, which we published last year in Physical Review A. So it works like this. So Alice and Charlie are both given a two-mode squeeze vacuum state, or an EPR state, and they propagate one mode towards, so Alice propagates one mode towards Charlie, and Charlie propagates one mode towards Bob. And then there are two quantum scissors, which increase the entanglement of these two links with probabilities that scale like the square root of the transmissivity of the channel. And it's the square root because the repeater has cut the channel in half. So quantum memories are required to hold on to those quantum states so that the total probability of success of the entire protocol, instead of being like the probability of the first quantum scissor times the probability of the second quantum scissor, the total probability is just the probability of one of the quantum scissors. So this is really important that we have quantum memories to hold on to the quantum states. And lastly, the dual homonyte measurement is the Bell state measurement that performs the entanglement swapping. So how does this protocol perform? So on the left, I have the secret key rate as a function of distance. For two different protocols, this is just if Bob decides to do homonyte detection or heterodyne detection. Okay, so yeah, performance, how does it do? So we beat the repeaterless bound between 300 and 400 kilometers. And if we look at the ultimate bounds for the well-known protocols, so we're not doing so well because we're down here. So we've lost about 100 kilometers compared to twin field. But the scaling is still as we expect for the single repeater bound. So we know our repeater is an effective repeater. So this is kind of the main result of the talk, and that is that the quantum scissors are actually tolerant to loss. So if you put loss inside the device, I realized that the scissor still works on certain input states quite well. So specifically if the input state isn't very, is quite Gaussian, or if it's a thermal state particularly, then it still performs pretty good noiseless linear amplification on the state, even if there's a whole lot of loss inside the device. And there's a new gain. So the gain of the quantum scissor, it used to be the square root of Bob's beam splitter transmissivity divided by 1 minus the transmissivity of the beam splitter. But once you put loss in the device, then so if the transmissivity of this loss is eta b, then this is the new gain. So for more loss in the scissor, that increases the gain. So this is the main result of the talk, which allows us to improve the protocol that I just introduced on the previous slide. So what it means is that we can actually move the measurement part of the quantum scissor into Charlie's station. And that means we don't need all of these components. So what I mean is because usually we're using this as a noiseless linear amplifier to distill entanglement. But if you can put loss here, that means that the detector actually forms a repeater in itself. And if I put this part at Bob's station, then basically I've moved the measurement from this quantum scissor into Charlie's node, and I'm doing entanglement swapping and noiseless linear amplification at the same time, if you like. So it means I don't need all of the other components. So this is our new protocol. So in case you're a bit lost, I'll just go through it step by step again. So Alice is preparing some state, so coherent states in a Gaussian distribution for QKD, or she might prepare in some entangled state or just any arbitrary state, and she's trying to send it to Bob. And so she sends it to a repeater node, Charlie. Bob prepares a single photon and entangles it with vacuum on a beam splitter with transmissivity TB and sends one mode towards Charlie. And Charlie should be about halfway between Alice and Bob. The gain of the repeater is set by this expression. So it's the square root of Bob's beam splitter transmissivity divided by the loss in the Bob-Charlie link times 1 minus his beam splitter transmissivity. So the success probability goes like square root of eta, which is the key point of this protocol, because the repeaterless bound scales like eta, but this protocol scales like square root of eta. So this means we can actually beat the deterministic bound in continuous variable quantum key distribution using this protocol, which will be quite an amazing result if we can do this in an experiment. So yeah, down the bottom, I've just got if you're trying to send a CV state. So this is the entanglement-based version. an entangled CV state. So how does it perform? Well, we beat the repeaterless bound at about 230 or 220 kilometers for the coherent state QKD protocol. And for the realistic curve, I have dart counts, 10 to the -8 rate, and I also have inefficient single photon sources and detectors of 75%. And there's also excess noise as well. So the best direct transmission protocol for coherent states is shown by the black line. And yeah, and I've also got the ultimate bounds. So our protocol scales in the right way, and we beat the repeaterless bound, the PLOB bound. So comparing these rates to our much more complicated repeater with quantum memories, we do much better now because we used to beat the bound at 300 kilometers and now we beat it just after 200 kilometers. So not only is this protocol much more simple in terms of resources, we also have improved the key rates. So a nice thing about this is that quantum scissors generalize to higher order. So for example, shown on the left is my 3 scissor from a paper I published last year. So it works by Bob preparing a 3 photon number state and mixing that with vacuum instead of the single photon. And then in the repeater station, he just has to look for 3 clicks instead of 1 click. And then you have this little array of beam splitters and phase shift as well. So on the right, so the success probability goes like, we obviously lose the success probability because you're waiting for 3 clicks. So the success probability scales like eta to the 3 on 2. So you can't beat the repeaterless bound using this. In fact, you don't even scale like the repeaterless bound. So it scales pretty not that well. But by putting the loss here, actually, we've improved the key rate because it usually scales like eta to the 3, but now it's eta to the 3 on 2. So when we first came up with this new scissor, like the referees weren't very happy with it because the success probability was so bad. But here we've improved the success probability. So this is a really nice result. And on the right is a measure of entanglement, the Gaussian entanglement of formation. So for the single photon repeater, the entanglement only goes down slightly with distance and then becomes some constant value. And the 3 photon repeater distills more entanglement at the cost of a greater success probability. Sorry, worse success probability. And just for comparison, if you set an infinitely squeezed EPR state, CV 2-mode squeeze state, then you lose entanglement exponentially with distance. So everywhere in this gray region, you can't access without a probabilistic protocol. So I have some nice plots just to prove to you that our repeaters are working in CV. So suppose you have a random input state and we plot the Wigner function, which is just the phase quasi-probability distribution. So it's a function of the position of momentum in phase space. So it's just some crazy input state. And after 20 meters of loss, the state has contracted towards the vacuum state and a lot of the non-Gaussianity is washed out. And then suppose you use our single photon repeater with 25 meters loss inside the repeater. So now the total distance between Alice and Bob is 50 meters. Then you can see that the non-Gaussianity is sort of returned and the state is amplified a little bit. And if you use the 3 photon version, then the state looks even closer to the initial input state. And this is for a crazy non-Gaussian input state. So for Gaussian input states, the repeater works really well. Okay, so our repeater also scales to longer chains. So on the bottom of this slide, we have our original protocol with quantum memories. So 3 repeater stations dividing the channel into 4 sections between Alice and Bob. So we used to need 8 quantum memories, 4 quantum scissors, 4 two-mode squeeze states, 3 dual homodyne detections, 6 displacements, and a lot of back and forth communications. But with our new protocol, we just need 4 quantum memories and 3 quantum scissors. So it's a much more simplified scheme. So I've calculated secret key rates for the repeater chain. And you can see that we scale like the 3 repeater bound. We even beat the single repeater bound in the ideal case. And for realistic experimental parameters, it seems to work pretty well as well. So I can imagine that something like the top, something like this figure might not be too far away experimentally, since you just need, a couple of photon detectors and photon sources. So it seems manageable compared to the figure down the bottom. So the reason why we care so much about the key rate is because consider the plob bound. If you're scaling like the transmissivity of the channel and you want to go 1,000 kilometers, by scaling like the 3 repeater bound, you've improved the key rate by many, many orders of magnitude. And this is why it's so important to have repeater stations if you want to go long distances with quantum communication. So in summary, the most important result of the talk is the fact that quantum scissors are loss tolerant, which means that you can use the measurement part of the scissor as a repeater station in itself, because you can put loss on this mode in the scissor. So this means we can overcome the plob bound in continuous variables without quantum memories. And so I like to think of this analogous. This is like analogous to quantum error correction when you break even for the first time. So I think it'll be a really nice result if in the future, sometime soon, someone does this experiment in CV, because it's been done in DV, but not in CV. So this protocol generalizes to higher order, which means that you can use a higher order scissor to keep more terms in the state that Alice sends to Bob at the cost of a higher or a worse success probability. Our protocol also generalizes to a repeated chain for longer distances. And future work is to investigate fully measurement device independent protocols. And we want to know if it's possible to approach the single repeater bound or not.